This is SpaceTime, Series 29, Episode 19, for broadcast on the 13th of February 2026. Coming up on SpaceTime, have astronomers just seen a black hole explode? How dust storms have helped Mars lose some of its water? And using what's called a plasma tunnel to recreate the extreme conditions of atmospheric reentry. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers are double-checking their observations after seeing what appears to be a black hole exploding. And if it did, it could explain almost everything. Back in 2023, a subatomic particle called a neutrino crashed into Earth with such high energy that it should have been impossible. In fact, there's no known source anywhere in the universe capable of producing that amount of energy, around 100,000 times more than the highest energy particle ever produced by the Large Hadron Collider, the world's most powerful particle accelerator. However, physicists have recently hypothesized that something like this could happen when a special kind of black hole, one they call a quasi-extremal primordial black hole, explodes. In new research reported in the journal Physical Review Letters, the authors not only account for the otherwise impossible neutrino, but they show that this elementary particle could reveal the fundamental nature of the universe. Black holes exist, and we have a good understanding of their life cycle. A large high-mass star runs out of fuel, explodes as a core-collapse supernova, and then leaves behind an area of space-time with such intense gravity that nothing, not even light, can escape, hence the term black hole. Alternatively, a stellar mass black hole can also be formed when two really high-mass stars merge together, again collapsing to form a black hole. Now, in both these cases, these stellar mass black holes are incredibly massive and essentially stable. But there's another kind of black hole, a primordial black hole, which could be created not by the collapse of a star, but from the universe's primordial conditions shortly after the Big Bang 13.8 billion years ago. Now, primordial black holes exist only in theory so far. And like regular stellar mass black holes, they're so massively dense that almost nothing can escape them. However, despite their density, primordial black holes could be much lighter than stellar mass black holes so far observed. Furthermore, primordial black holes could slowly emit particles through so-called Hawking radiation. That's if they get hot enough. One of the study's authors, Andrea Pham from the University of Massachusetts, says the lighter a black hole is, the hotter it should be and the more particles it should emit. As primordial black holes evaporate, they become lighter and lighter, and so theoretically hotter and hotter, emitting more and more radiation in what eventually is a runaway process until ultimately they explode. She says that Hawking radiation is something our current telescopes are able to detect. And it would be an important detection, because if such an explosion were observed, it would actually provide scientists with a definitive catalogue of all subatomic particles in existence, including the ones we've observed, such as electrons, quarks, and the Higgs boson, but also the ones we've only hypothesized, like dark matter particles, strange exotic quarks, as well as lots of stuff which is so far entirely unknown to science. Pham and colleagues had previously shown that such explosions could happen with surprising frequency. They speculate every decade or so. And if we were to pay attention, our current cosmos-observing instruments could register these explosions. In 2023, the KM3-NET collaboration captured that impossible neutrino we spoke about at the start of our story. And it's exactly the kind of evidence the authors hypothesized that we would see. Problem is, there was a hitch. A similar experiment called IceCube down in Antarctica, which is also set up to capture high-energy cosmic neutrinos, not only didn't register the event, but it hasn't clocked up anything that even came close to this level of power. Now, if the universe is relatively thick with primordial black holes, and they're exploding frequently, then we should be showered with these high-energy neutrinos. And that raises an important question. How does one explain this discrepancy? Pham speculates that primordial black holes with so-called dark charge, what her study calls quasi-extremal primordial black holes, are the missing link. The dark charge is essentially a copy of the usual electric force as we know it, but which includes a very heavy hypothesized version of the electron, which Pham and colleagues are calling dark electrons. The authors say there are other simpler models of primordial black holes out there. But this new, more complex dark charge model, they speculate, may provide a more accurate model of reality. BAM says a primordial black hole with a dark charge would have unique properties and behave in ways that are very different from other simpler primordial black hole models. She says not only can the dark charge model primordial black hole explain the neutrino, it can also answer the mystery of dark matter. Observations of galaxies and the cosmic microwave background radiation all suggest that dark matter exists. And if this hypothesized dark charge is true, then there could be a significant population of primordial black holes out there, which would be consistent with other astrophysical observations and account for all the missing matter in the universe. This is Space-Time. Still to come, how dust storms may have helped Mars lose some of its water, and using a new experiment called a plasma tunnel to recreate the extreme conditions of atmospheric re-entry. All that and more still to come on Space-Time. This episode of Space-Time is brought to you by Squarespace, your all-in-one website builder that makes it simple to create, share and grow your presence online. Now let's talk about one of our listeners, Emma. She's a science communicator who started hosting small science workshops at her local community hall. But when word started to spread, she knew she needed a professional online presence and she needed it fast. And that's why she turned to Squarespace. Emma built her website in just one weekend. With Squarespace's easy tools, she listed her upcoming events and let people book tickets online. No awkward email chains, no manual payment schemes. The built-in scheduling feature sent out automatic confirmations, and she even used Squarespace's email marketing to remind attendees about new events. Everything looked clean, on brand, and totally professional. And here's the kicker, people started finding her site straight away through Google. You see, Squarespace's SEO tools were working quietly in the background, optimizing her pages so her workshop showed up when locals searched for science events near me. Now, Emma's workshops are booked out months in advance, and it all started with a professional online home built on Squarespace. And if you're ready to create your own story, go to squarespace.com/spacetime for a free trial. And when you're ready to launch, use the promo code SPACETIME to save 10% of your first purchase of a website or domain. That's squarespace.com/spacetime with the code SPACETIME, and you'll find the link in our show notes.
This is Space-Time with Stuart Gary.
A new study may show how an unusual dust storm on Mars may help explain how the red planet lost some of its water. Our current image of Mars is an arid, hostile, freeze-dried desert. But that contrasts sharply with the history revealed by the planet's surface. When you look at Mars, there are clear signs of channels, minerals altered by water, shorelines and beaches, and other geological traces which indicate that the red planet, at least in its early days, was a much warmer, wetter place and a far more dynamic world. Reconstructing how this water-rich environment disappeared remains one of the great challenges of planetary science. Although there are a number of processes that can help explain this water loss, it can't explain all of it. The fate of much of the Martian water, therefore, remains a mystery. Now a new study in the journal Communications, Earth and Environment has brought science at least a little step closer to solving that puzzle. For the first time, scientists have demonstrated that an anomalous, intense but localized dust storm would be capable of driving the transport of water to the upper layers of the Martian atmosphere during the Northern Hemisphere summer, a time when the process was previously considered to be irrelevant. One of the study's authors, Adrian Bryans from the Institute of Astrophysics in Andalusia, says the findings reveal the impact of this type of storm on the red planet's climate evolution, and so it opens a new pathway for understanding how Mars lost much of its water over time. While dust storms have long been recognized as important for Mars's water escape, previous discussions have mostly focused on large planet-wide dust events. In contrast, this new study shows that smaller regional storms can also strongly enhance water transport to higher altitudes, from where it can then more easily be lost into space. And while previous research has focused on warm dynamic summers of the southern hemisphere, since this is typically the main period of water loss on Mars, this new study detected an unusual increase in water vapor in the middle atmosphere of Mars during the northern hemisphere summer back in 2022 and 23. That was caused by an anomalous dust storm. In fact, at these altitudes, the amount of water was up to 10 times greater than usual. a phenomenon not observed in previous Martian years and not predicted by current climate models. Shortly afterwards, the amount of hydrogen in the exobase, that's the region where the atmosphere merges with space, increased significantly to 2.5 times that of previous years during the same season. One of the keys to understanding how much water Mars has lost is measuring how much hydrogen has escaped into space, since hydrogen is readily released when water breaks down in the atmosphere. So the new observations are adding a vital addition to this incomplete puzzle of how Mars has been losing its water over billions of years. And it shows that short but intense episodes can play a relevant role in the climate evolution of the red planet. This is SpaceTime. Still to come, scientists and aerospace engineers are now using a new high-energy test facility called the Plasma Tunnel to recreate the extreme conditions spacecraft experience during atmospheric reentry. And later in the science report, a new study claims your genetic background probably has the greatest single impact on your life expectancy. All that and more still to come on SpaceTime. Scientists and aerospace engineers have started using a new ultra-high energy test facility called the Plasma Tunnel to recreate the extreme conditions spacecraft experience during atmospheric re-entry. When a spacecraft returns to Earth, the vehicle slams into the planet's atmosphere at roughly 28,000 kilometers per hour. That generates a powerful shock wave. Molecules in the air are ripped apart. That forms a plasma, a gas made up of charged particles that can reach tens of thousands of degrees, many times hotter than the surface of the sun. Now, this is a spectacular sight to behold, but it's also very dangerous. The Space Shuttle Columbia disaster was a tragic example. Back on the 1st of February 2003, as the orbiter re-entered Earth's atmosphere, plasma flooded into the vehicle through a defect in one of the carbon-carbon leading-edge wing panels, which formed part of the shuttle's protective heat shield. Once inside, this heat quickly melted structural components. The space shuttle disintegrated. Its 7 crew members, 6 Americans and 1 Israeli, were killed in the tragedy. Finding new ways to combat this heat developed during atmospheric re-entry has been a primary goal for engineers and scientists ever since. One of those is Hashim Ali from the University of Colorado Boulder. He says re-entry is one of the most critical and dangerous phases of any space mission. Vehicles hit hypersonic speeds when they pass Mach 5, that's 5 times the speed of sound, and at sea level that's a blistering 6,200 kilometers per hour. So engineers are trying to recreate the wild physics that occur at these speeds entirely from the safety of the ground. To do that, Ali and colleagues have developed a new kind of research facility called the inductively coupled plasma tunnel. The complex generates streams of plasma that flow at speeds of hundreds to thousands of kilometers an hour and burn at up to 5,000 degrees Celsius or hotter. This one-of-a-kind facility can test how new materials and other technologies behave in such extreme conditions. One of the ideas they're now exploring is whether they can use powerful magnets to maneuver vehicles flying at hypersonic speeds. That's something not possible today, but it's something they're already testing at the new Plasma Tunnel Lab at the university's Boulder East campus. There, a 40-kilowatt generator powers the plasma wind tunnel, a quartz glass tube about the size and shape of a wine bottle. It feeds into a much larger chamber, sealed with stainless steel several inches thick. In an instant, a lavender-coloured light blinks on in the quartz glass tube. The eerie glow comes from the plasma, like the kind which threatens a spacecraft as it returns to Earth. From there, the plasma rushes into the metal chamber, which you can peer into through a porthole window. Inside the chamber, every surface radiates orange from the heat. Now, to simulate the conditions of hypersonic flight, the group needs 2 things, speed and heat. To build up speed, technicians inject a stream of argon gas into their tunnel. A powerful vacuum system then sucks the gas through the tunnel quickly. In fact, the vacuum can pull more than 20,000 cubic meters of air an hour, making it one of the most powerful machines of its kind in the United States. Engineers then hit their plasma with strong radio waves that flip back and forth. These generate electric currents within the gas, eventually causing it to explode into a plasma. Once the argon's lit, the team can then inject regular Earth air into the tunnel. They then use a metal arm to lower test materials into the plasma flow. And the streaming plasma instantly forms a shock wave around the object. Engineers can then test how different materials behave under these extreme conditions. The authors are now tackling what might be the most persistent challenge of hypersonic flight. See, once a vehicle hits those sort of speeds, it's virtually impossible to steer. Now, we all know Russian President Vladimir Putin claims the Kremlin's newest hypersonic missile can do this already. But the problem is anything that sticks out of a plane or spacecraft, or missile for that matter, travelling at those sort of speeds, like wings or flaps, burns up almost at once. As a result, pilots can't easily change a spacecraft's trajectory once it re-enters Earth's atmosphere from orbit if something goes wrong. And Putin's hypersonic missiles shouldn't be able to turn on a dime like he claims. The new plasma tunnel will help determine whether he's telling the truth. One possible way around the limitation could be magnetism. You've got to remember, plasmas are made up of charged particles. So if you have a powerful enough magnet, you can potentially change the flow of those charged particles around the vehicle, much like you can use a toy magnet to move around iron filings. So the engineers are envisaging a future where spacecraft, and missiles I guess, could employ ultra-strong magnets to push plasma shockwaves around them. Maybe that's the secret Putin's found. Ali says the process might build up enough force to turn a vehicle at least a little bit.
Spacecraft that enter or exit the atmosphere inherently encounter a hypersonic flight regime. Really navigating the challenges of hypersonics and flying in that way involves solving a lot of new and difficult engineering problems to achieve that type of flight. The vehicle is actually going so fast that the air in front of it doesn't have time to get out of the way. So you might go from a temperature of 200 degrees centigrade to 20,000 degrees centigrade within that shock wave. When you heat air to that type of temperature, it ceases to become air as we know it, only oxygen and nitrogen, but it instead starts to chemically react and it starts to dissociate. It may even form a plasma. Plasma may experience effects due to electric and magnetic fields because it is electrically conductive. So now an individual plasma particle may experience forces due to, yes, collisions between themselves or the wall, but also these bulk field effects. And that opens up a lot of interesting avenues for maybe being able to control the flow with those electric and magnetic fields. We are trying to primarily replicate the heating environment. We take a lot of power and we concentrate it into a plasma beam. And then what we do is we might get a coupon or a test article of some representative sample from a hypersonic vehicle. And then we actually insert that into the flow, and then we observe what happens to it. So if it's a heating test, we might be measuring the temperature, we might be measuring the heat flux, we might be measuring the time until failure. It's about improving access to space. It's also about improving our knowledge as a species. So a lot of planetary exploration missions, when we send probes to other planets like Mars or Venus, we have to go through their atmosphere. And we have to provide mission assurance and safety for that science payload. And reentry remains a very dangerous phase of those missions. And so a lot of research goes on, both theoretical, computational, and in the end, experimental to qualify and prove those systems to enable us to explore the solar system.
That's Hashim Ali from the University of Colorado Boulder, and this is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study claims your genetic background probably has the greatest single impact on your life expectancy. The findings, reported in the journal Science, aim to disentangle death from natural causes and those from other causes using mathematical models, simulations of human mortality, and multiple large-scale studies that use twins data. They found the human lifespan is actually far more heritable than previously believed. The analysis showed that once deaths from external factors, such as accidents or disease, are accounted for, genetics may explain at least 50% of how long you're likely to live. Well, it looks like time is almost up for how we track each second of the day, with new advances of a new optical atomic clock technology coming to fruition. Optical atomic clocks are made from laser-cooled trapped ions and atoms. When scientists repeatedly probe the atoms with a laser, they respond only at specific frequencies, which can then be converted into ticks and tocks to track time accurately. Researchers from Adelaide University, the United States National Institute of Standards and Technology, and the British National Physical Laboratory have been reviewing the future of these next-generation timekeepers. Their report in the journal Optica found that optical atomic clocks will become the gold standard for timekeeping within the next few years, provided that some of the remaining technical challenges can be addressed. Optical atomic clocks are far more accurate than the best microwave clocks and can even work beyond the lab, a place where conventional atomic clocks have trouble. And they can also be used as gravity sensors, which can aid in creating an international height reference system that's not based on sea level. A new study has found that saltwater crocodiles found in the Indian Ocean's Seychelles Islands have the same DNA as salties found thousands of kilometres away in Vanuatu in the Pacific Ocean. The findings, reported in the Journal of the Royal Society Open Science, combine genetic data from modern samples with mitochondrial genomes from historical museum specimens of the genus Crocodylus porosus, including material from Seychelles crocodiles which were wiped out by humans some 200 years ago. The study shows that crocodiles on that remote archipelago didn't belong to a separate species as previously thought, but simply represented the westernmost population of the current existing estuarine or saltwater crocodile. Among all living crocodiles, the salty is the best adapted to life in the ocean. For example, they have special salt glands which allow them to excrete excess salt and survive for long periods in salt water. This enables the species to colonize islands and coastal regions over thousands of kilometres. Well, time now for what seems to be our regular Bigfoot segment. And despite thousands of people out there working hard to find Bigfoot, the 8 to 10 foot tall Sasquatch remains as elusive as ever. Now, mind you, there have been lots of anecdotal reports, lots of unprovable witness claims, loads of footprints, and heaps of squatch blobs, blurred images of the beastie. But actual scientifically verifiable evidence, such as DNA, roadkill, physical remains, they're all still lacking. But as the skeptic's Tim Mendham points out, that hasn't stopped towns across America celebrating the legendary Sasquatch.
Bigfoot is a thing in America. Actually, there's supposed to be Bigfoot everywhere in the world, but in America, very big. There's one that's just recently launched itself in Michigan called Keweenaw. Don't know how to pronounce that, but the Keweenaw Peninsula, which they're claiming is a hotspot for Bigfoot, mainly because they're promoting a festival they've got coming up. Now, Michigan is a long way from northwest USA, where most Bigfoot supposed to be happening, but that doesn't stop someone in Michigan deciding that their festival is the best thing since sliced bread. And so you find these festivals all over America. You find Bigfoot sightings all over America. You find the same lack of evidence all over America. And wherever you supposedly have these big feet wandering around. But maybe it'll turn up and maybe that'll be a great thing. But I somehow doubt it.
That's the skeptic's Tim Mendham, and this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.